Now let's do merge sort. So the idea behind merge sort is this. If you have two sorted lists, and these are both sorted, it is very easy to combine these into a new sorted list. So let's say we started with a list with 8 items unsorted like this. What merge sort is going to do is first break this list in half, and break it in half again, and break it in half again, until the only thing that we have left are lists that only have one item in them. So there will be 8 separate lists with one item in each list. And a list with one item in it is by definition sorted. So now that you've gotten these all down to single item lists, we can take 2 of the items and create a new list that's sorted. And we'll do that with the next 2, and so on until we have 4 lists in this case with 2 items each. Then we'll do it again with these 2 lists like that, and with those 2 lists. And now we can take these 2 lists and combine them into one sorted list. And that is our high-level overview of merge sort. So in this video, we're going to talk about our merge function. Merge is what is called a helper function. It doesn't do all of what is required for merge sort, it just does a portion of it. So the portion that merge does is it takes 2 sorted lists, and they do need to be sorted lists, and it takes the values from these and puts them into a new combined list like this. So let's put this back like this and walk through how we would do that. So we're going to loop through each of these lists, and we'll loop through the first one with a variable I, and the second one with a variable j. Then what we'll do is just compare I and j. Whichever one is lowest, we will add to the new combined list. Then we'll do it again. In this case, j is lower, so we'll add that one. Then we just keep going through, making these comparisons, and we do this until one of the lists is empty. Once we've done that, we'll have another loop that loops through whichever list still has items, and we'll add these items to the combined list. So we will code this helper function in the next video, but for now, that is our introduction to merge. So now let's write our code for our merge function. So we'll start with our 2 sorted lists like this. I'll shrink these down. And we'll start this out by saying merge, and then we're going to pass it 2 lists. They both have to be sorted. And we're going to combine these 2 lists into a new list. And I'm going to call that list combined. Now, one of the key things here to figure out in combining these is you can't use for loops, because you don't know how many you're going to take from each list to begin with. We're going to have to use while loops. So I'm going to declare the variables for our while loops as I. We'll set that equal to 0. And that points to the index of 0 in our first list. And then we'll say j equals 0, and we'll do the same thing for the second list. And then our while loop is going to look like this. And this is basically saying, as long as both lists still have items in them, we're going to run this while loop. If either list becomes empty, it'll break us out of this while loop. So in this case, I is less than j. We'll start out with this to say if I is less than j, these 2 items, and it is in this case, into the combined list, we're going to append from list 1 the item at the index of I, like that. Then we need to move I over 1. We'll do that like this, I plus equals 1, and that moves I over. Now we're going to run through the while loop again and compare I and j. In this case, j is less. We're going to say else, and do the same thing here. Into the combined list, we're going to append from list 2 the item at the index of j. And then we need to move j over 1. We'll do that like this, j plus equals 1, and that moves j over. And as we continue to loop through this while loop, it'll look like this until that second list is empty. And remember, we only run this until one of the lists is empty, and that'll break us out of this while loop. So now we need to get the 2 items left in list 1 into the combined list. So let's look at doing that. We'll say while I is less than the length of list 1, we'll append those items to the combined list at the index of I, and we need to move I over like this, and then we'll do it again. And now list 1 is empty, and that breaks us out of this while loop. The other possibility is that we had items left in list 2, so we'll need an almost identical while loop for list 2 that'll look like this. So we'll run the first while loop if list 1 still had items remaining. We'll run the second one if list 2 still had items remaining. And now the only thing left to do is to return that combined list. So now let's look at this in with the rest of our code like this, and that is the entire merge function. So now let's go take a look at this in VS Code. So there's our merge function there, and I'll scroll this up. And then down here, we're going to run the merge function with these 2 lists and print out the result. So I'll run this. And that gives us a single combined list with all 8 items in order. And that is our function for merge. So in the last video, we created merge that takes 2 sorted lists and puts them together. Now we're going to look at merge sort that also needs to take a list and break it in half, and then break it in half again, and then do it again. Once we've gone through this process of breaking it in half, it is only then that we can use that helper function, merge, to take sorted lists and combine them, like this. And then we'll do it again and do it again to create the sorted list. So what we're going to do here is write the code that breaks lists in half. And this is going to be the first time that we've used recursion. Remember, we had 2 rules for being able to use recursion. First, it has to do the same thing over and over. And this is just going to break lists in half over and over. So it meets that criteria. The second criteria is that you have to be making the problem smaller. Well, if you're breaking things in half, then by definition, you're making things smaller. So this is a perfect place to use recursion. And we're going to use the recursion until we reach a base case. And the base case is going to be when we've broken it down to where the length of the list is 1. So once we've done our recursion to break things in half, we've reached our base case to stop breaking things in half when we've gotten down to 1 item. That is when we'll use merge, which we created in the last video, to put the list back together. So these will be the 3 steps of merge sort. Break it in half until we get it down to 1. Then we use merge to put everything back together. And that is our quick overview of merge sort. So now we're going to write our code for merge sort, and we'll start our code off like this, and we're going to pass it this list. And on the right side of the screen, I'm going to bring in a call stack, and I'm going to add an instance of merge sort to the call stack. So merge sort is going to be called recursively, so we're going to have multiple instances of merge sort on the call stack. And each instance is going to be called with a list. So to keep track of what list each instance of merge sort was called with, I'm going to do this. So now we're going to split that list in half. And in order to do that, we're going to need a midpoint. We'll call that mid index. And we're going to set the mid index to be equal to the length of the list divided by 2. So in this case, the length is 4 divided by 2 is 2. Now, one of the things we have to do here is to account for when we have an odd number in the list. So for example, if we had a list with 3 items in it and we divide by 2, we're going to get 1.5. And we can't have an index of 1.5. So we're going to change this into an integer. And in the situation where the mid index would be 1.5, everything to the right of the decimal place would be dropped and the mid index would be 1. But in this situation, because we have 4 items, the mid index is 2. And that is this index here. So I'm going to take that 2 and store it next to this instance of merge sort. That's mid index for this instance. So now we're going to create 2 new lists. The first one we'll call left. We'll set it equal to my list on this range. So when you do a range like this with this colon, whatever's on the left, that's the starting point. If you don't have anything on the left, the starting point becomes the first item. And we go up to, but not including the index that's on the right of the colon. So mid index is this. And when we go up to, but not including, we're going up to this index. So left is going to be a new list with these 2 values in it. And then we'll do the same thing on the other side. We'll say right equals my list on this range. So on the left of the colon, we have mid index. That's the starting point. That will be here. And if we don't have anything on the right of the colon, we just go to the end. So that means we're going to create a new list with these 2 values in it. So left and right will be these 2 new lists. Then we call merge. That's the helper function that we wrote in the last video, and we call it on left and right. But there's a problem here. Merge only works on sorted lists, and neither one of these lists is sorted. What we need to do is break each of these lists in half, and we do that with these 3 lines of code. And specifically, the splitting happens with this code here. And this did exactly what it was supposed to do. We just need to do it again. So this is where we call merge sort recursively. So now let's take these 2 lists, put them back together, and we're going to start this over. So we've already calculated the mid index. We know that's the index of 2. And then when we come down here, this portion of the code does exactly what it did before. It's just going to create this new list with 2 items in it. The difference is we're going to call merge sort on that new list. So we'll add this to the call stack with this list. So now this becomes the active instance on the call stack. So for this instance of merge sort, we're going to start out by calculating the mid index on this list. So the length of this list is 2, divided by 2 is 1. This is going to be the mid index. So then we come down to this line, and this portion here is going to create a new list of just 1 item. And I color this green because a 1 item list is by definition sorted. But we're going to call merge sort on that list. We'll add this to the call stack on this list. And since this list has 1 item in it, we don't want to run these 3 lines to try to break the list in half. This is our base case. So we're going to say, if the length of the list is 1, and that is the case here, we're going to return my list. So in this return statement, where does it return it? It's going to return it to the function that called it. And once the return is run, this gets popped from the call stack. So now this becomes the active instance on the call stack again. And this was the last line that it ran. So it ran this in order to determine what left would be for that instance of merge sort. So I'll put this back, and now we'll move to this line. So this portion here is going to create this list, and we're going to call merge sort on that list. And now this becomes the active instance of merge sort on the call stack. The first thing we'll do is check to see, is the length equal to 1? It is, and we're going to return my list, and this gets popped from the call stack. So this becomes the active instance of merge sort on the call stack again. We just ran this line, and this 1 item list is right. So now we move down to here, and we're going to run merge on left and right. So we'll add this to the call stack on left and right, and that's going to do this. So this line here, I'm going to remove the return to show what this does. So the merge function has a return statement in it. So where does it return to? It returns to here. And once it runs that return, this instance of merge gets popped from the call stack. So now this is the active instance, but it has this return statement in here. It's going to return whatever merge returned to it, which means it's going to take this list and return it to here. And once it does that, that is popped from the call stack. So now this is the active instance on the call stack. We just ran this and determined that left equals this sorted list. So I'll put this back, and we'll move to this line of code. So remember, this is being called on that 4 item list. So right is going to be these 2 items, so that right side of that 4 item list, except we're going to call merge sort on it. We'll add this to the call stack, and it's being called on this list. So now this becomes the active instance of merge sort on the call stack. We're going to check to see if the length is 1. It is not. So now we'll calculate mid index, and that's going to be this item. And then we move down to here. This portion is going to create this 1 item list. We're going to call merge sort on that. And now this becomes the active instance. We'll check to see if the length is 1. It is, and we'll return my list, and this gets popped from the call stack. So now this is the active instance again. We just determined that this 1 item list is going to be left. Now we move to here. So this portion here is going to create this 1 item list, and we're going to call merge sort on that 1 item list. And now this becomes the active instance. We'll check to see if the length is 1. It is. We'll return that 1 item list, and this gets popped from the call stack. So now for this instance of merge sort, we have determined left and right. Now we move down to here and call merge on left and right. We'll add this to the call stack with both of those 1 item lists. And that does this, and I'll do that same thing where I remove the return. Merge is going to return this list to here. That gets popped from the call stack. But this instance of merge sort, because it has this return, is going to take this list and pass it down to here. And when it does that, it gets popped from the call stack. And I'll move this back up here. And now this is the active instance again. We have found left and right for this instance of merge sort, which are these 2 sorted lists. Now we move down to here. And we're going to run merge on these 2 lists. We'll add that to the call stack on these 2 lists. And that is going to do this. So I'll remove that return from the code again. Merge is going to return this list to here, and that is popped from the call stack. But because this instance of merge sort has this return statement, it's going to return this somewhere. And the place that this gets returned to is the original function call. It's going to return it to here. And once it does that, this instance of merge sort is popped from the call stack. And now we have this sorted list. So we'll look at this code in a moment in VS Code, and when we do, we'll start out with a list that looks like this, and we'll run merge sort and return a sorted list. So now let's flip over and take a look at this. So there's our merge sort function there, and I'll scroll up. So this is going to be the list that we pass to merge sort, and I'm calling this original list. And then I'm going to have a separate list called sorted list that is equal to merge sort on the original list. So merge sort is different than the other sorting algorithms that we've seen so far. The other sorting algorithms sort the list in place. That is to say that the original list will be sorted when we're done. But with merge sort, the original list stays the same, and it returns a separate sorted list. So now I'll run this, and you can see that our original list is unchanged, and there's a separate sorted list that was returned. And that is our function for merge sort. Now let's look at the big O of merge sort. Let's bring up a list here, and the first thing I'm going to talk about is space complexity. So with merge sort, you start out with this original list. Then you create two new lists called left and right, and then you continue breaking these down. So you start out with your original list, and then you have 8 new lists that each have a length of 1. So the number of items being stored in memory have been doubled. So that means this is O of n for space complexity. The previous sorting algorithms that we've looked at are sorted in place. That means we take the original list and we move things around inside of that list. Merge sort is different than that in that it creates new lists. So let's put this back up here and look at time complexity. When we're breaking this in half, we do this in 1, 2, 3 steps. We had 8 items. It took us 3 steps. This is going to be log n because 2 to the third power is 8. It took us 3 steps to break this in half with 8 items. But let's look at what happens when we put these together like this. So think back to our merge function, our helper function. It had those while loops in there that went through each number one by one to be able to combine these into a sorted list. So breaking these apart is O of log n. Putting it back together because of having to loop through each item with the merge function is O of n. And so that's where we get the O of n times log n time complexity for merge sort. So let's look at this on the graph. And when it comes to sorting algorithms, only the 2 on the left really matter. I'm going to gray out the ones on the right. The first 3 sorting algorithms that we created were O of n squared, bubble sort, insertion sort, selection sort. But this one is much more efficient, O of n times log n. O of n times log n is the most efficient that you can make a sorting algorithm that's going to sort multiple types of data. There are certain efficiencies in sorting only numbers, and there are some sorting algorithms that can run more efficient than this, but you can only sort numbers with them. But if you're going to sort multiple types of data, this is as good as it gets. So O of n times log n is much more efficient than O of n squared. And it may not look that way on this graph, but the axis on the left, the y-axis, only goes up to 75. If the axis went to 1,000 or it went to 1,000,000, you would see that there's a huge difference between O of n squared and O of n times log n. And that is our overview of merge sort, big O. So now let's look at our overview of quicksort. We'll start out with a list like this, except I'll put it like this. And the way quicksort works is we start with a pivot point. That's going to be that first item. Then we're going to compare each of the numbers after that to this to see if it's greater than or less than. So we start with the 6. The 6 is greater than, and I'll color that in gray. The 1 is less than. I'll color that in yellow. All the less thans will be yellow, and the greater thans will be gray. And then what we're going to do is swap that 1 with the first item that was greater than, like this. Then we move to the 7. We'll color that in gray. The 3 is less than, and we'll swap that with the first item that was greater than, which is the 6, like that. The 2 is less than, and we'll swap that with the 7 because the 7 is now the first item in the list that is greater than the 4, like this. And then the 5 is greater than. So we have all of the items that are less than the 4 together and all of the items that are greater than the 4 together. And then in the next step, we'll swap the 4 with the last of the less than items like this. So 2 things to point out here. First, the 4 is now sorted. I colored that in green. And everything less than the 4 is to the left of the 4. Everything greater than the 4 is to the right of the 4. And then what we're going to do is run quicksort again on these items as well as on these items. We'll start on the left first. 2 will be our pivot in this case. 1 is less. The 3 is greater. Then we swap these 2 items and now the 2 is sorted. Then we'll run quicksort on these 2. And because there's only 1 item in each of these, we know those are sorted. Then we'll run quicksort on this side. The pivot is going to be 6. 7 is greater. 5 is going to be less. We're going to swap these. And then we'll swap these. The 6 is sorted. We'll run quicksort on these. And because there's only 1 item in each of these, we know these are sorted. And now we have a completely sorted list. And that is our quick overview of quicksort. So in this video, we're going to walk through how our pivot function is going to work. And pivot is going to be a helper function that we use for quicksort. So this is similar to how we use the merge function as a helper function in merge sort. So to explain it, I'm going to bring up a list, except we'll show it like this. And what we're going to do in pivot is we're going to pick a pivot point. That's going to be the first item. Then we're going to have all the items that are less than the pivot value on one side and all the ones that are greater on the other side. And then we'll swap these. And this makes it where that 4 value is in the spot where it will be when the list is sorted. So pivot is going to do 2 things. It's going to get the list to this point where it looks like this, but it's also going to return the index of that 4 value. And we'll talk about why we're going to return the index instead of the value in a moment. But for now, I'm going to put this back like this, and we'll walk through how we're going to make this work. So we're going to have a pivot value, and then we're going to compare it to everything after that with a for loop. So the for loop is going to start here. We're going to call the variable in the for loop I. We're also going to have a variable that points at this pivot point. The variable is actually going to be called pivot index, but I'm just going to say pivot on the arrow here to make it fit. And we'll have another variable called swap index. I'll just call it swap on the arrow here also to make that fit. And then we'll start running through the for loop. So the first value for I is greater than the pivot value, so we'll just color that in gray. and then I moves to the next index. Now this one is less than, so what we're going to do is move swap over 1, and then we'll swap the values at swap index and I, like this. Then I will move forward again. This one's greater than. This one is less than the pivot index value. So we'll move swap up 1, and then we'll swap these two values. This is also less, so we'll move swap up, exchange these two, and then we get to the end of the for loop, and we're done with the I variable. So then what we're going to do is swap the items at the pivot index and the swap index like this. That puts 4 in the correct spot, and the only thing left to do is return that index, that swap index that is pointing to the 4. And this is everything that the pivot function is going to do. And the reason we return the index is when we run quicksort again on this side, we're going to do it from the beginning up to but not including the swap index. And then on the other side is going to be the swap index plus 1 to the end. So that is why we need to return the index. So we'll start coding this in the next video, but for now, that is our overview of pivot. So now we're going to write the code for our pivot function. So first I'm going to bring up a list like this. We'll represent it like this, and we'll shrink that down into the corner. So one of the things about this function is we have two different places where we need to swap items inside of the list. And we would swap those items with something like this. But since we're doing it twice, I'm going to create a function called swap so we don't have to rewrite this code. And we're going to use this in two different places in our pivot function. And that will just clean things up a bit. So let's get into the pivot function itself. So we're going to pass this a list, but we also need to give it the pivot index and the end index. So what we're going to do here is we're just going to pass it the first index of 0 and the end index, which is going to be 6. So we have 7 items here. It'll be 0 through 6. So we've already created our first variable up here, pivot index, and that's going to point here. Our next variable, swap index, will just set that equal to the pivot index like this. And then that variable I was part of our for loop. We'll bring that in for I in range, and it's going to need the pivot index and the end index for this for loop. So I is going to start out at pivot index plus 1. That's going to put it here. And then here we say end index plus 1. And remember, the reason for that is the for loop is going to go up to but not including this value. And that's why we need to add the plus 1. So then we're going to compare that first value of I to the pivot value. So we'll say if my list at the index of I is less than my list at the pivot index, well, in this case, it's not less than. So I'm not going to fill out this if statement yet. What I'm going to do is color that value in gray, and then we'll run through the for loop again, which moves I over 1. So now this if statement is true. So now there are two things that we want to do. We want to move that swap index over 1. We'll do that like this, swap index plus equals 1, and that moves that over. And then we want to swap the items at I and at swap index. So we'll do that like this. This is that function that we created at the beginning of the video. We'll pass it the list, the swap index, and I, and we'll swap those two items. Now, if we continue running this for loop all the way to the end, our list is going to look like this. Now what we need to do is swap the items at pivot index and swap index. And to do that, we're going to use that function again that we created at the beginning where we swap two items. We'll just swap the items at pivot index and swap index, and that will do this. Now the only thing left to do is return the swap index. So I want to emphasize here, we're not returning the value of 4 here. We're returning the index of 3. So the pivot function does two things. It's going to rearrange the items in your list so they'll look like this, and it will also return the swap index. So we'll look at this code in a moment in VS Code, and when we get done running it, our list is going to look like this with 4 in the middle. All the items that are less than will be on the left. Everything that's greater than the 4 will be on the right. But we're going to start the list out looking like this. All right, so now let's flip over to VS Code. So there's our swap function there that just takes two items in the list and exchanges them. Here's our pivot function. And then down here, we've created a list called myList. This is the list that we just looked at. And then we're going to run pivot on myList. And then the pivot index is going to be 0. That's the first item in the list. And then the end index in the list is going to be at the index of 6. Okay, so I'll run this. And remember, the only thing this returns is the swap index of 3. But we also want to make sure that our list has been rearranged the way we want it to be rearranged. So we're going to come down here and paste this in where we print myList after we run pivot. So I'll run this again. And you can see here that 4 is in the middle, and all the items that are less than 4 are on the left, and all the items that are greater than 4 are on the right. All right, so that is our function for pivot. So now let's create our quicksort function. So remember, quicksort is going to use pivot, which is going to create a pivot point and then make the list look like this. Then it's going to return the index of this item. What the quicksort function is going to do is recursively run pivot again on this side, and then run it also on this side. So let's put this back the way it was, and we'll shrink it down, and then we'll start writing our function. So we'll call it quicksort, we'll pass it a list, and we have to have the leftmost index and the rightmost index for quicksort, and that's going to be 0 and 6 to begin with, that we're going to pass this. So this next line of code, there's going to be quite a bit going on here. Okay, so first, this is a variable that stores the index that the pivot function returns. So we're going to call this pivot index, and we're going to set it equal to the pivot function, and we're going to pass it these 3 variables. So remember, pivot is going to do two things. The first thing it does is going to rearrange everything in the list to look like this. The second thing it does is it returns this index. So in this case, we're going to assign that index to the variable pivot index. Now, once we've done this, we need to recursively call quicksort on the left. We'll do it like this. We're going to pass it the same list, but with a different range. It's going to go from left, which was 0, up to pivot index minus 1, which will be this range here. And then we will also recursively call this on all the items on the right. So it's the same list, myList, but it's pivot index plus 1 all the way to the right index, which was the index of 6, which is this range here. So let's bring this up and focus on this. Let's focus on the left one first. We will start with this. This one's less. This one's greater. We'll make this exchange, and this will cause us to recursively call quicksort on the left and the right. There's only one item left in each of these, so we're going to stop calling quicksort, and we know those are sorted. Then we'll do this on the right, where this is our pivot point. This one's greater. This one's less than. These get switched. Then we do this, and then we recursively call quicksort on each side like this, and everything is sorted. So I'm going to shrink this down like this and bring our code back. The thing we haven't done here is created our base case. So these three lines only are run if left is less than right. So if you look at left and right up here, we began with left being 0 and right being 6. Left is less than right. If we ever get to the point where left is greater than right or left is equal to right, we want to stop running this code. And that is our base case. And then the only thing left to do is to return the list. So we'll look at this code in a moment, but we'll start with a list that looks like this. So let's flip over and take a look at this in VS Code. So there's our swap function, and the swap function was used inside of the pivot function. And we'll scroll up here. And the pivot function was a helper function that we're using here inside of the quicksort function. So we'll call quicksort down here with that list that we just looked at. And the beginning index is going to be 0, and the ending index is going to be 6. So I'll run this. And there we have our sorted list 1 through 7. So now that we have this code written, I'm going to make a change, because what we don't want to do is have to pass the beginning and ending index every time that we call this. So we're going to take this quicksort function and just rename it to quicksort underscore helper. And there are a couple places that we're going to have to rename this inside the function here, because this is where it gets called recursively. So we'll change this to underscore helper. And then we're going to change this to underscore helper. And then what I'm going to do is paste in this function. And you can see now we can just pass this the list. Then we can come down here to where we call the function, and we don't have to pass it these two indexes. We can just pass it the list. And this line here we'll call the quicksort helper. It'll pass it my list, but it'll also figure out what the first and last index is. So this makes it where anyone that is using this function can just call quicksort, pass it the list. So I'm going to clear this output, and then I'll run this again. And you can see this is still returning 1 through 7. But the advantage being that we don't have to pass this the beginning and end index when we run it. And this is the version I'm going to include in the attached code for this section. All right, so that is our function for quicksort. Now let's look at quicksort big O. Let's bring up our list here. So the first step with quicksort is to run pivot. When we run pivot, our list ends up looking like this. And if you'll recall, in the pivot function, we had a for loop that went all the way through the list, looking at each item. That process of running pivot is going to be O of n. But the recursive part, we've done one step here. Here's 2 steps and 3 steps. So let's say we have approximately 8 items here, and we did this in 3 steps. 2 to the 3rd power is 8. We've seen this before. That's O of log n. So quicksort is O of n times log n, just like merge sort. And on the graph, that is much more efficient than O of n squared. But the n times log n for quicksort is actually just for the best case and the average case. The worst case is not n times log n. So let's take a look at that. Our worst case is if we already have sorted data. So we start out with our pivot point being that 1. We're not going to move anything else in the graph, and that one is going to be sorted. And normally we run quicksort on everything on the left and everything on the right. But we only have items on the right. So we're going to run pivot on everything else again. Remember, pivot is O of n. So we're going to do this again, and then we're going to do it again all the way down. So we're running that pivot function on every single item. So that O of n function pivot, we're running it n times in order to get this sorted. In other words, this is O of n squared if you have already sorted data. So O of n squared is actually the worst case with quicksort. So long as you don't have sorted data, you know you're going to have data that is very out of order. You can count on it running in n times log n times. But if you have sorted data, it might be better to use something like insertion sort. So we saw earlier that insertion sort is generally O of n squared, but the best possible scenario for insertion sort is O of n. So that becomes one of the things you have to consider when you're looking at sorting algorithm, big O. So now we're going to do tree traversal. And what tree traversal is that we're going to visit every node in the tree, and we're going to take the values and put them in a list. And then we'll return that list. But tree traversal is a little more complicated than doing something like a linked list, because with a linked list, because it's just linear, if we're going to traverse this, we just start at the beginning, and then we just go through the list. But with a tree, there were multiple ways to visit each node. We could do something like this, where we start at the top, and then we do the next row like this, and then we do the next row like this, and so on. This is called breadth first search. Another way that we could do this is we could start all the way to the bottom left, and then come up, and then come down, and then come up to the first item, and then go all the way to the bottom left of the items remaining like this, and then come up, and then come down. And this is an example of what is called depth first search. And we're going to look at 3 different ways of doing depth first search. But for now, that is our quick overview of tree traversal. So in this video, we're going to look at the steps to do breadth first search. So breadth first search was the one where we would start at the top, and then do the second row, and then the third row straight across, and so on. So I'm going to move this over, and the way we're going to do this is we're going to create 2 lists. The first one we're going to call Q, and the other one is going to be called results. Results is going to be the one we return with all of the values of the nodes. But with the Q, we're going to start at the top, and we're going to store this node in the queue. So it's an important point here that we're storing the entire node in the queue. We're storing not just the value of 47, we're storing the left and the right as well. So I'm going to change this to look like this. I'll keep this as blue to emphasize that this is the entire node. So we're going to do something with the value and the left and the right. So to begin with, the value, we're going to move it down to results. I changed this to green because in the results list, we are only storing the value, not the entire node. And then for the left and the right, we'll start with the left. We're going to store the node from the left of the 47 in the queue. And then we'll do the same for the one on the right. And then we'll go through the same 3 steps with the value and the left and the right with the 21. We move the value down to results. To the left of the 21 is 18. To the right of the 21 is 27. And then we do the process again. The 76 gets moved down here. 76 has a node to the left, which is the 52. And it has one to the right, which is the 82. So when we do the process this time, we have a value, 18, but 18 doesn't have anything on the left or the right. So then we move to the 27. The same is the case with that, as well as with the 52 and the 82. So the loop that we're creating to do this will only run as long as the queue has items in it. So now that the queue is empty, that means that we've visited every item in the tree. And the only thing left to do is to return this results list. Now there's something else that's interesting about breadth first search. Let's look at just the numbers in this list. If you take the first one and put it here, and then you take the next 2 in the list and you put them here, you can see that this is an exact replica of the tree. So those are the steps, and in the next video, we will code breadth first search. So now we're going to write the code for breadth first search. So we're going to bring up our tree like this. I'll shrink it down to the corner, and then we'll begin our method. So I want to point out that this is a method in the binary search tree class. So this is not a separate function. So that's why we have the self keyword there. And then we have a few variables that we need to create. First, we'll say that current node is equal to self.root. I've highlighted that in green on the tree there. And then we're going to need a queue. I'm going to implement this as a list. So if you'll recall from when we created the queue data structure, a list is not the ideal way to implement a queue from a big O perspective. But the reason I chose it here is everyone by this point in the course is very familiar with lists. So I want to use what's most familiar here so we can focus in on the mechanics of creating the breadth first search. So we'll bring in the queue here. And then the other thing we need to create is a results list. I'll bring that in like this. And then we need to take that current node and put it into the queue like this. We'll say queue.append current node. So remember, this is the entire node, the value and left and right. So then I'm going to represent that node that we put in the queue like this as a blue number. So we know that that's the entire node, not just the value. And it's very important that you put this node in the queue before you start your while loop, because the while loop is going to run as long as the length of the queue is greater than 0. In other words, it's going to run until the queue is empty. If you don't put the first node in there, the while loop will never run because it will start out by being empty. So let's focus in on the while loop and build this part out. So the first thing we're going to do is set that variable current node to be equal to the first item in the queue. And remember, this is the value and left and right. So first, let's do something with the value. We'll say results.append current node.value. So we're not putting the entire node in there. It's just the dot value portion. So now let's look to the left of that node. We'll say if current node.left is not none. In other words, if there is a node to the left of the current node, then we're going to say q.append current node.left. So we'll append the node to the left of the current node like this. And then we'll do the same thing on the right. If there's a node on the right, we're going to do q.append the node on the right, which is the 76. So then we go up and run the while loop again. So these 2 lines here, as we move through this while loop and repeat this, I'm going to combine these. So we're going to pop that first item off, and then we're going to append the value into the results list. So then the 21, we're going to look to see if it has an item on the left. That's going to be the 18. We'll append that to the queue. And then the item on the right will append that. Now we run the while loop again, and we move the 76 down to the results, and we look to the left of the 76 and add the 52 to the queue. And then to the right of the 76, we append the 82. Now we run the while loop again, and now we have the 18. Now the 18 doesn't have anything on the left or on the right. Same is true for the 27 and the 52 and the 82. So now our queue is empty, and we were only running the while loop while the queue had a length greater than 0. So we're done with this. We're done with the while loop. The only thing left to do is return that results list. So let's look at this in with the rest of our code like this. This is the entire method for breadth first search. And we'll look at this in a moment in VS Code. And when we do, we'll create this tree, and we'll expect to see this list returned. Okay, so let's go take a look at this in VS Code. Okay, so there's our method there for breadth first search. I'm going to scroll to the top here. And I want to emphasize that this is a method inside of our binary search tree class. So I'm going to scroll back down here, and there's our method again. And I'll scroll up a little more. This is going to create that binary search tree that we just saw. And we're going to print mytree.bfs, breadth first search. And we would expect it to return this list here. So I'll run this. And you can see that this list up here matches this list down here. And then something else I wanted to point out here is that list that was returned is in the same order that we created the tree here. Okay, and that is our method for breadth first search. So I had mentioned in the first video for tree traversal that there would be 3 types of depth first search that we would look at. The first one that we're going to look at is going to be pre-order. I'm going to bring up a tree like this. And with pre-order, the order that we're going to add the numbers to the list will be like this. We'll start at the top, we'll add the 47. And then after that, we're just going to keep moving to the left. So we'll put the 21 into the list and then the 18. And this is as far as we can go to the left. So we're going to come back up to the 21 and go to the right there. And now we've looked at everything to the left of the 47. So now we'll go right. And then after the 76, we always go left first. We'll come down to the 52, come back up to the 76 and down to the 82. And that is the order that those will be added to the list. And we'll code this in the next video, but that is our intro to pre-order depth first search. So now we're going to code depth first search pre-order. So I'm going to bring up our tree here, the same one we've been working with. But for this, I'm also going to bring up a call stack. So we'll start out our method like this, DFS pre-order. Remember, this is a method inside of the binary search tree class. And we're going to have a results list that we're going to return. I'll bring this up from the bottom like this. And the next thing we're going to do, we haven't seen this before, but inside of a method, you can have a function. I'm just going to bring in the function is a recursive function, and we're going to call it traverse. And I'm just going to move this up so we can focus on this. So we're going to pass traverse a node. And the first thing we'll do is take the value from that node and write it to the results list. Then if there's a node on the left, this is where the recursion happens. We're going to run traverse on that node on the left. Then if there's one on the right, we're going to run traverse on the node that's on the right. And the way we kick all this off is we call the function with the root. And when we do, it pushes an instance of traverse onto the call stack. In this case, we'll say that's the node with the number 47. That's the instance that we're talking about. And that instance of traverse, the first thing it's going to do is append the value of that current node, the 47. Then it's going to look to the left to see if there's a node. And if there is, it'll run traverse on that node. That's the 21. Now that gets pushed onto the call stack. And because 21 is at the top of the call stack, that is the instance of traverse that is running now. So the first line of that instance of traverse is going to append the number 21 to the results list. And then that is going to look to the left. And there is a node on the left. That's the 18. That gets pushed onto the call stack. And now it is going to append its value to the results list. 18 doesn't have anything on the left. It doesn't have anything on the right. So now we can pop that from the call stack. Now the 21 is at the top of the call stack again. It's already gone left. Now it needs to go right. So the node on the right of the 21 is the 27. First thing we do is we append that value to our results list. The 27 is going to look left. It's going to look right. There are no child nodes to the 27. So now we can pop that from the call stack. Now the 21 is the top of the call stack again. It has gone left. It has gone right. And now we can pop that from the call stack. So now the 47 is at the top of the call stack again. It's already gone left. Now it needs to go right. So now we're going to run traverse on the 76 node. First thing we're going to do is append the value of the 76 node like this. And then we're going to go left. That's the 52 node. We'll push that onto the call stack. First thing we do is run this line. We'll append that value to the results list. 52 is going to look left and right. It does not have any left or right children. So we can pop that from the call stack. The 76 has already gone left. Now it needs to go right. That'll push the 82 onto the call stack. We'll run this line, which adds 82 to the results list. It's going to look left and right. There's nothing on the left or the right of the 82, so we can pop that. The 76 has gone left and it has gone right. So now we can pop that from the call stack. And the 47 was the first item on the call stack. It'll be the last one off. It has gone left. It has gone right. So now we can pop that off the call stack like that. And that was the original function call when we said traverse self.root. That was with the number 47. Now the only thing left to do is return this results list. So now let's look at this with the rest of our code like this. And that is the entire method. So we'll look at this code in a moment in VS Code, and we'll build this tree. And when we run this, we would expect to get this list returned. All right, so now let's flip over to VS Code. So there is our method there. And I'm going to scroll up. And this creates our binary search tree that we just saw. And this will run depth first search preorder on that tree. And we would expect to get this list here. Okay, so I'll run this. And it looks like that has returned what we have expected. All right, and that is our method for depth first search preorder. Now let's look at depth first search post order. I'm going to bring up a tree here. In this video, we'll just walk through the steps of it, and then we'll code it in the next video. And just like with all the other tree traversals, we're going to start at the top. What's different here is that we're just going to visit that 47 node. We're not going to write that value to the results list yet. Then we're going to go to the left and then visit the 21, and we'll go to the left again to the 18. Now what the 18 is going to do is it's going to look to the left. There's no node there. It'll look to the right, and there is no node there. And then finally, it will write its value to the results list. So the order that we're doing this is we look left, we look right, and then we write the value from that node. So now we come up to the 21. It has gone left. Now it's going to go right to the 27. It's going to look to the left. It's going to look to the right. And then finally, we will write the value 27 to the results list. Now we come back up to the 21 again. Now it has gone left. It has gone right. Now we can write that value to the list. And that brings us back up to the 47. It has gone left. Now it will go right to the 76 node. And we always start with going left first. So it will go to the 52 node. It will look left and right and then write its value. We come back up to the 76. It has gone left. Now it will go right. That 82 node will look left and then write its value. That brings us back up to the 76. It has now gone left and right, and it can write its value. And that brings us back up to the 47. It has gone left, it has gone right, and now its value can be written to the results list. So we'll code this in the next video, but that is our overview of depth first search post order. So now let's write our code for depth first search post order. We'll bring up our tree here and our call stack, and then we'll start writing our method by saying dfs post order, and then we'll create our list results that we're going to return at the end of this, and I'll bring that up from the bottom here. And with depth first search preorder, we had a function called traverse. We're going to do the same thing here. And I'm going to start by bringing in the exact same traverse function. So this is exactly the way you would write traverse for preorder. So in preorder, we wrote the number to the list, and then we went left, and then we went right. But for post order, we're going to go left first, and then right, and then append the value to the results list. So we have all the same code. It's just in a different order. So I'm going to move this up like this, and we'll kick this off by running traverse on the root. And when we do, that gives us an instance of the traverse function that is added to the call stack. Now 47 is going to look to the left first. There is an item on the left. That's the 21 node. So now we're going to run traverse on the 21 node. The 21 node has a node to the left, which is the 18 node, so that will get added to the call stack. The 18 node is going to look to the left, then it will look to the right, and then finally it will append its value to the results list like this. And once it does, we're done running that instance of traverse, so we can pop that from the call stack. Now the 21 is at the top of the call stack again. It has already gone to the left, now it can go to the right. And there is a node on the right, the 27 node, so we'll add that to the call stack. The 27 node is going to look left, it will look right, and then finally it will append its value to the results list like this, and then we can pop that from the call stack. So now the 21 is at the top of the call stack again. It's already gone left, it has already gone right. The only thing left for the 21 to do is to append its value to the results list. So we'll do that, and then we'll pop 21 from the call stack. So now the 47 is at the top of the call stack again. It has already gone left, now it can go right. So now we'll run traverse on the 76 node, and the 76 node will look to the left to see if there's a node there. There is. The 52 node, so we'll add that to the call stack. The 52 will look left, it will look right, and finally append its value like that, and we can pop that from the call stack. The 76 has gone left, now it can go right, so we'll add the 82 to the call stack. It will look to the left, it will look to the right, and then finally append its value to the results list like that. We'll pop that from the call stack. Now the 76 is at the top of the call stack. It has gone left, it has gone right, now it can append its value to the results list like that, and we'll pop that from the call stack. And then finally, the 47 node, the one we kick all of this off with, it has gone left, it has gone right, and now it can append its value to the results list like this. And now we can pop that one from the call stack, and that was the original function call. So now the only thing left to do is to return the results list. So now let's take this code and add it in with the rest of our code like this. And that is our entire method for depth first search post order. So we'll look at this in a moment in VS Code. And when we do, we'll create this tree, and then we'll expect to get this list returned. All right, so let's flip over to VS Code. So there's our depth first search post order method there. And I'm going to scroll up. And this is going to create that tree that we just looked at. And this is where we'll run depth first search post order on that tree and print out the results. And when we do, we would expect to get this list here. All right, so I'll run this. And that gives us the list that we were expecting. All right, so that is depth first search post order. Okay, so now let's look at depth first search in order. We'll bring up our tree like this. And what we're going to do is we're going to visit that first node. We're going to go to the left again. The 18 will try to go to the left. There's nothing there. We'll write that 18 to our results list, and then it'll go to the right. So at this point, the tree looks exactly the same as it did at this point with depth first search post order. But instead of going left, then right, and then writing its value, it's going left, writing its value, and then going right. So we're going to get this in a different order. So now we're going to come up to the 21. It has gone left. Now it's going to write its value and then go right. The 27 will go left, write its value, and then go right. That brings us up to the 47 node. It has gone left. Now we can write its value and go right. The 76 will start out by going left. The 52 will go left, write its value, and then go right. The 76 has already gone left. Now we can write its value to the results list and then go right. Then the 82 will go left and then write its value and then try to go right. So at this point, what I'm going to do is turn the entire tree back to blue and look just at the order that the items get written to the list. We start out with the 18 being written to the list, and this is the lowest value in the tree. Then it's the 21, the next lowest, and so on. Then the 47, the 52, and the 76, and the 82. So all of the numbers are written to the list in numerical order. So that is depth first search in order. So now we're going to code depth first search in order. So we'll bring up our tree and our call stack, and we'll start writing our method depth first search in order. And we'll create our results list like that. So now I'm going to bring in the traverse function that we used for depth first search pre-order. In that one, we appended the value to the list, then we went left, and then we went right. In post order, we went left and then right and then wrote the value. For in order, we're going to go left, we're going to write the value, then we're going to go right. So once again, we have the exact same code, just in a different order. So I'm going to move this up like this, and we're going to call traverse on the root. And that is going to add an instance of traverse with the 47 node to the call stack. And the first thing we're going to do is go left, and that adds the 21 to the call stack. And now the first thing that instance of traverse is going to do is go left, and that's going to add the 18 to the call stack. And the 18 will try to go left, and there's nothing there. And then it will write its value to the results list like this. Then it will try to go right, and there's nothing on the right, so we'll pop that from the call stack. Now the 21 is at the top of the call stack again. It has already gone left. Now it will write its value to the results list like this. And then the 21 is going to go to the right. And so we'll add the 27 to the call stack like that. First thing the 27 will do is look to the left, and there's nothing there. And then we'll write its value to the results list like this, and then it will look to the right. And now that one is done, and we can pop that from the call stack. Now the 21 is at the top of the call stack again. It has already gone left, it has written its value to the list, and it has gone right. So now we can remove that from the call stack. The 47 now is back on top of the call stack. It has gone left, and now it can write its value to the results list like that, and then it can go to the right. So we'll add the 76 to the call stack. It will go left to the 52. The 52 will look left. It will append its value to the results list, and then it's going to look to the right. There's nothing on the right, so we can remove the 52 from the call stack. Now the 76 has already gone left. Now it can append its value to the results list like that, and then it will look to the right. We'll add the 82 to the call stack like this. It will look to the left. We'll append its value to the results list. It will look to the right, and now we can pop that from the call stack. So with the 76, we've already gone left and appended its value and gone right, so now we can remove that. And the same is true for the 47. It has gone left. We've added its value to the results list, and it has gone right, and we can remove that from the call stack. And that is the original function call where we call traverse on the root. And now we just need to return the results list like that. So now let's look at this in with the rest of our code. And that's our entire depth first search in order method. And we'll look at this in a moment in VS Code. When we do, we'll create this same tree that we've been using, and we will expect this list to be returned. All right, so let's flip over to VS Code. So there's our depth first search in order method. And I'm going to scroll up here. And this is going to create our binary search tree that we've been looking at. And then down here, we'll run depth first search in order on that tree and print out the results. And we'll expect to see this list returned. Okay, so I'm going to run this, and that returns our list in order. All right, and that is our method for depth first search in order. So now we're going to code depth first search in order. So we'll bring up our tree and our call stack, and we'll start writing our method depth first search in order. And we'll create our results list like that. So now I'm going to bring in the traverse function that we used for depth first search pre-order. In that one, we appended the value to the list, then we went left, and then we went right. In post order, we went left and then right and then wrote the value. For in order,